Learn like a pro.
So how do you deal with chemical chaos? You know, when you've got this jumble of different liquids all mixed up and you need to get them apart. Well, today we're going to master the one simple tool that lets a chemist do exactly that. I mean, you've totally seen this before, right? You shake up oil on water and for a second you get this cloudy mess. But just give it a moment and poof, they separate. Okay, so it's not really magic. What you're seeing is a fundamental principle, and it's the key to a really powerful technique in chemistry. So this one little experiment actually shows us two huge ideas. On the left, you've got what we call miscible liquids. You can think of them like best friends. They mix together perfectly into one uniform liquid. But then, on the right, that's our oil and water situation. These guys are immiscible. They just plain refuse to mix, and you can see that super sharp line right between them.
All right, so let's lock in that term, immiscible. Basically, it just means that when you put these liquids together, they form what's called a heterogeneous mixture. They don't mix evenly. If you just leave them alone, they'll always settle into their own separate layers, which we call phases. And that stubborn refusal to mix, that's the exact property we're about to take advantage of.
So the big question is, why does one float and the other one sink? Well, it all comes down to one word: density. The best way to think about it is like stacking books. The heaviest, densest one always goes on the bottom, right? And the lighter ones go on top. It's exactly the same with liquids. The liquid with the higher density sinks, and the one with the lower density, it floats. Simple as that. This is a basic rule of physics, and it's the secret sauce that makes this whole separation thing possible.
Okay, so if density is the rule of the game, who's the referee that enforces it? Well, let me introduce you to the perfect tool for the job, the separating funnel.
You know, the real genius of this thing is how simple it is. The absolute key part is this little valve down at the bottom. It's called a stopcock. Because that heavier, denser liquid naturally settles right on top of it, this one little tap gives the chemist complete, and I mean precise, control. You can literally drain that bottom layer one drop at a time if you want. It is all about control. Okay, so we've got the why and we've got the what. Now let's put them together and talk about the how. It's a super simple, kind of elegant procedure. Here's the play-by-play for pulling off a perfect separation. Honestly, this process couldn't be any simpler. It's just 3 steps. Step 1, settle. You just pour your mixture in and you wait. Let it sit until you see that really sharp line between the layers. Step 2, drain. You open up that stopcock and carefully let the bottom layer, the dense one, flow out into a beaker. And then step 3, and this is the most important part, isolate. The very second that line dividing the two liquids gets to the tap, you slam it shut. And boom, that's a perfect separation.
All right, so now that we've got this technique down, let's kind of zoom out a bit and see where this fits into a chemist's overall game plan.
But what if our little density trick doesn't work? I mean, what happens if the liquids are miscible? What if they mix up completely? Well, a separating funnel is totally useless in that case. So chemists have to switch up their strategy. They have to find a different physical property to take advantage of. Like, say, their boiling point. And the tool for that job is a completely different technique called fractional distillation. And that really brings us to the chemist's strategy guide, or you could call it a cheat sheet. It's super simple. Are your liquids immiscible? Do they form layers? Great. Use a separating funnel. Are they miscible? Do they mix all the way? Okay, then you need to use fractional distillation. It really is all about knowing what kind of mixture you have and then just picking the right tool for that specific job.
So when you boil it all down, the main takeaway is this. Separating chemicals isn't magic. It's all strategy. It's about finding some physical difference between the things you're trying to separate, whether it's density or their boiling point or something else entirely, and then just picking the right piece of equipment that lets you take advantage of that difference. So that leaves us with a cool question, right? What other physical properties do you think you could use to bring a little bit of order to all that chaos?